nostalgia. Habrá de ser un tango nuestra herida, un acordeón sangriento nuestras almas.
Welcome back to Your Brain, a Personal Tour. Today's seminar is about the decision to act. Whereas Hamlet had it easy, he only had to make a decision about whether to revenge his father or not. In everyday life, the decision to act is much, much more complicated. We're going to talk about the 4 ways your brain makes a decision. Some are pre-wired by Mother Nature, some rely on mental time travel, and some are so habitual we don't even think about them. Each type gives us unique insights into our brain, so I hope you enjoy the seminar. I begin with some background on this quote. Amelia Earhart was dubbed Queen of the Air. She was the first female soloist across the Atlantic. She was a best-selling book author and married to a famous book publisher, George Putnam. She was also a strong advocate for equal rights. Fierce determination marked Amelia once she had made a decision. That's why she's on the slide today. She tragically died in 1937 on a circumnavigation flight around the planet due to a memory problem. But memories are the next seminar. We'll talk about decisions right now. While Hamlet had it easy, life presents us with everyday demands that require decisions, and they begin at a very early age. Let's take a look at an example.
The marshmallow test is a really great way to show how children delay gratification. We tried it out with the 4 children we've been following since September 2010, Alfie, Millie, Mackay, and Pratmesh. Here's how it works. We had each child on their own sit at the table at a desk with a plate and 1 marshmallow. They could either choose to eat the marshmallow, the 1 marshmallow, right then and there, or they could wait until I came back into the room and have 2 marshmallows. I left them alone in the room for 15 minutes. Take a look. The marshmallow test has been used for decades by psychologists. It's been used with children to predict later academic success, including literacy, SAT scores, and other academic outcomes. There's no definitive answers from the marshmallow test. It's not a matter of passing or failing. What we're looking for is whether children can really resist this piece of white candy sitting in front of them that's sweet, that, the smell of it, the allure of the marshmallow. In Pratmesh's case, we really saw this added curiosity because he had never actually tasted a marshmallow before. All of the children managed to show some level of self-control and resist the temptation to eat the whole marshmallow. As you can see from the footage, you can catch a glimpse into children's ability to control their impulses. This ability, which is developed around the time of kindergarten, can be linked to other outcomes later in life. At the end, the marshmallows were in kind of different states. Some had been squished, ripped apart, nibbled around. There was this temptation and there was this impulse to kind of try it out.
This video is typically presented as an example of delay of gratification or an exercise in self-control. I think now that you've seen what the children actually did, you'll recognize that they're deciding not to eat the marshmallow by deciding to do something else. Much of the socialization and choices we are presented with in life are not simply delays of gratification. It's deciding to do one set of actions rather than another. I said there were 4 ways such decisions are made. Let's look at each one of them in turn. The first kind of decision is a reflex. It's a decision that Mother Nature has pre-wired into your brain because this decision is too important for your brain to deliberate. It's a stereotypical behavior, typically of a defensive nature, and it's designed to protect you, to keep you alive. But don't get the idea that only simple movements are reflexes. They can be complex. Let's take a look. One way a reflex comes into play is a reaction to physical harm. Whenever one of your limbs hits a painful stimulus, the leg in this example, a withdrawal reflex rapidly moves the limb to minimize harm. On this diagram, you've just stepped on something sharp. They're specialized receptors called nociceptors that detect the harm, transmit a signal to your spinal cord, and via a pre-wired path, adjust your body to withdraw. First, muscles are both activated and relaxed so that you can bring your foot away from this sharp and painful stimulus. But notice what also happens. Your other leg is simultaneously prepared to handle the shift in weight. Your brain is informed, but that will take a bit of time. You're gonna feel the pain long after you've moved your limbs. So you don't think, you react. And most of the time, that's a very good thing. Don't get the idea reflexes are just for jerking your limbs. They can be a whole body experience and emotional. For example, the freezing response of the rat is a reflex. This is an immobilization of the rat coupled with several internal emotional responses. For example, higher blood pressure, faster heart rate, etc. A reflexive way to elicit this behavior is the smell of coyote urine. The wisdom of this act and of Mother Nature is obvious. The essential point here is that reflexes are not just about stubbing your toe. They can underlie some complex behaviors. Like moral judgments. Here we study the actions of 6-month-old infants to the actions of geometric shapes. Now the shapes must have eyes for this experiment, and that's important. The infants watched a plucky little circle try to scale a mountain. My, oh my, how the circle tried, but he just couldn't do it. A triangle helped the circle get to the top, but the mean old square, the blue square, pushed the circle back down the hill. Infants reliably reached for the helper geometric shapes rather than the hinderer geometric shapes, thus performing what many would say is a moral judgment of the character of that shape. But wait, it's a little more complicated than that. Reflex emotional behavior may even underlie behaviors of community. In this experiment, 9 to 14-month-old infants were observed to record their preference for either graham crackers or green beans. I know what you're thinking, but 47% of the 9-months-old preferred green beans, but by 14 months, only 31% liked the green beans, so they're getting smarter. Then the infants observed 2 hand puppets, and the hand puppets expressed food preferences. The puppets liked either crackers or green beans. When the infants were given a choice of reaching for one of the puppets, they invariably chose the puppet with the same food preference. That's to say, they preferred the us of a puppet liking a similar food to the infant. Then, the helpful or hurtful shapes with eyes were brought into the experiment, and the shapes interacted with the puppets. Babies love to see a food us being helped, and conversely, a food them being hindered. So this is not about infants preferring helpers. This is about infants preferring agents that are similar to them and preferring agents that hinder puppets that are different from them. We will talk about the implications of this later. Just one more point on the importance of eyes, on puppets or circles or whatever. There's something your brain pays attention to. And this is now being used in prototypes of driverless vehicles to protect pedestrians. The eyes really do have it. How to make sense of these somewhat surprising results on simple reflexes? The theory I subscribe to is that Mother Nature endows us with pre-wired emotional responses, kind of like the automatic mode on a modern camera. A simple, quick action that's appropriate for maybe 80% of the situations. As we age and encounter more complex and more social situations, our brains have evolved more advanced systems, like the manual mode on a camera. The advanced systems are very good, but they must be consciously and deliberately applied. We'll study those systems in just a minute. So let's let Homer take a crack at summarizing this section. The first thing Homer says is that reflexes are do it now. They are time urgent, no time for deliberation. They are very useful in avoiding or reacting to harm or threats with an automatic range of behavior. Those behaviors can be as simple as a knee-jerk and as complex as a moral judgment. However, reflexes can be overridden by kind of advanced manual mode We'll see more of that soon. This is especially important when reflexes seem to be out of place in the modern world. Let's take a look at our second type of decision. We'll call such decisions associative decisions. These decisions unleash a reflex-like behavior, but from a learned association. An association is a mental connection formed from learning. The science of such learned associations is uniquely associated with Ivan Petrovich Pavlov, shown here with the beard. Dogs were measured in their saliva response to food, which reliably elicited salivation, and to a lighter tone, which did not elicit salivation prior to training. When the light or tone predicted the delivery of food, dogs salivated to the light or tone. A learned association drove a decision. Such learning is often called classical conditioning or Pavlovian conditioning, and the decisions are termed associative decisions. They represent a fundamental type of decision-making by your brain and are actively studied even today. And I must note that my wife, Becky, is a professional dog trainer, so I know she'll be very proud of me for getting a dog into these slides. The dog of research today is the California sea hare. You see two of them here. These animals have a very simple set of behaviors. They basically move around in the sand, they squish water through a siphon, you'll see it disturb the surface of the water, and they use a gill to breathe. These animals are the perfect research animal for this type of decision learning. And they have illuminated the exact nature of how all brains learn such behavior. And they've even earned a Nobel Prize in the process. Well, not these two hares. The scientist Eric Kandel, who conducted the research, got the prize. The scientific name for this dude is Aplysia californica, and since he's from California, we're going to give him some cool sunglasses. But really, he's cool for one unique aspect of his brain. His brain has only a few cells, say about 20,000, compared to 86 billion in your brain, and they are huge. Many are visible to the naked eye. Neuron R2 is over 1 millimeter in diameter. It's roughly the size of the B in the Liberty Penny. These individual neurons can be uniquely identified visually. That means we can experiment with multiple different California sea hares, but study the same neuron in each individual as they learn and express associative decisions. So let's teach this dude a new trick and see what happens in his brain. We're going to use two stimuli. One will reflexively cause a behavior and is called an unconditioned stimulus, or US for short. In this experiment, it's a mild shock to the animal. Our guy will reliably retract his siphon to this US stimulus. The other stimulus is touching the animal. Normally nothing would happen. The guy would leave his siphon out and about. But if we pair that touch, called the conditioned stimulus, or CS, with a US of shock, we find that after training the animal for a while, there's a vigorous withdrawal of the siphon when we touch him. The animal has decided to withdraw a siphon since it is associated with shock. The key results are shown in the bottom right of the slide. Since we can see the brain cells of this guy, we can watch what happens to the exact neurons that underpin this change in behavior. We show a schematic of those brain cells in the top right. The L29 neuron on its own can activate the motor neuron which withdraws the siphon. That is how the shock causes the siphon to withdraw. A sensory neuron, corresponding to the touch CS, also converges on the motor neuron. But at first, the connection is not strong enough to evoke a withdrawal response. We know that after training, the sensory neuron can activate the motor neuron to withdraw the siphon. So what happened? Well, this happened. We have expanded our view of the connection between the sensory neuron and the motor neuron. What we see is the creation of a new path in the brain. This path is a combination of two changes. There's a short-term change where previously empty legs of the sensory neuron become filled with additional packets of neurotransmitter, the chemical that a neuron dumps on another neuron to get it to become active. Now, all of a sudden, the motor neuron is affected by the sensory neuron and the siphon begins to withdraw. Over the course of several hours, about 12 to 18, a dramatic event happens. There is actual growth in the brain. New legs appear on the sensory neuron, They become populated with neurotransmitter. Now there's a long-term structural change in the brain that reflects this learning. Should we say a memory? This change will now evoke the decision to withdraw the siphon to the tactile CS. So, short term, there's a transient chemical change, followed by a long-term, permanent structural change. Wow. So if our brain grows as we learn new information, does that mean we need a really big skull to be smart? Well, the Star Trek writers sure seem to think so. And in normal life, the skull actually does grow dramatically to accommodate a rapidly learning brain, but only to a point. Over the first 3 years of life, the skull almost triples in size. Man, that's a lot of learning, as any parent or grandparent could tell you. But after that, the skull size is relatively constant. So then, how do we learn new things if there's no room in the skull for increased brain circuits? Well, that's a problem, but it's a problem for memory, which we'll investigate in the next seminar. These same changes also happen in other organisms, like rats, and like us. These kinds of changes are important to understand. Let's take an example. We already know that a rat will freeze if you threaten her, say with coyote urine. She'll also freeze if you shock her foot. The pathway in the brain for that foot shock is shown on the right under the US label. Sensation for the shock goes through a couple of areas of the brain and then concentrates onto an area called the amygdala. The amygdala is a specialized structure in mammalian brains that detects, among other things, items that represent a threat to the organism. When the rat gets a foot shot, the sensation travels through her brain into the amygdala, which drives a behavior of freezing. But freezing isn't the only thing the rat does. There are internal changes to the rat. Her blood pressure goes up, stress hormones are released into her system, etc. After we associate the tone and the shock, the tone will elicit the external behavior of freezing, but also the changes in internal state, blood pressure rising, release of stress hormones, etc. In essence, the rat has an emotional response to the tone. Why do I say that? Research has shown that emotions are a response to internal bodily changes like heart rate, stress hormones, etc. You see this in the woods and bam, your amygdala is going to go crazy. It will prepare a flight or fight syndrome. Your blood pressure is going to go up. Stress hormones are going to be released into your bloodstream. Your heart is going to race. Based on a long set of psychological research, it is because your blood pressure is going up, because of your stress hormones being released, because your heart is racing, that you will report feeling fear. Stated another way, we feel fear not because we're looking at the bear, but because we're running from the bear. So this whole set of associative decisions is part and parcel of how we learn emotional responses to various stimuli. These emotional responses are automatic. They come as part and parcel of the associative conditioning process that is one way that emotions get attached to various things in our life. This concept of emotion can be used for treatments other than scaring people in the woods. Turns out that 20% of troops returning from Afghanistan or Iraq suffer from PTSD. Standard therapies only result in about 60% remission. The many members of the Special Forces report hypervigilance and anxiety, similar to the effects shown in the movie American Sniper. Well, if you block a specific autonomic nerve center or ganglion with a pain blocker, there are widespread reports of immediate and profound PTSD relief. One shot seems to block the emotion-generating aspect of high heart rate, fast breathing, and muscle tension. In other words, blocking the physical attributes that underlie emotion seem to release the perception of stress and allow therapy to progress. Let's ask Homer what he thinks about this whole set of associative decisions. Homer has 2 points to make. One is, even slimy sea thingies can learn to predict the future. Take an innocuous stimulus like a touch and pair it with a shock, and even a California sea hare can see the future. It will do something in anticipation of that shock, and that is an associative decision. The second thing Homer wants to say is that those kind of associative decisions change your brain, and it changes your brain with new growth. As we know, your brain is fully encased in bone, and that means it's within a fixed volume. If every time you learn something there's new growth in your brain, sooner or later it's going to run out of room. How does the brain deal with that? Well, it turns out that one of the prime functions of sleep addresses this, but we're going to learn about that later. Right now, we're going to explore the most complex decision making your brain can do. These kinds of decisions are called deliberative decisions. These are the decisions where we have to trade off priorities or options. We could do one thing or the other, and we evaluate the options before we actually decide and commit a particular behavior to action. Believe it or not, even our little friend the rat here goes through the same events in his brain. We'll see a rat's brain go through what can be thought of as mental time travel as he makes a deliberative decision. And what goes on in a rat brain goes on in your brain. Both our brain and the rat brain have structures that help us perform these kinds of activities. And to really get a good handle on this, we're going to have to look at 3 different places. So let's take them one by one. The first brain area I want to talk about is called the hippocampus. We see it here in a rotating model of your brain. It's the highlighted linear structure at the base of each hemisphere. It's about the size of your little finger. And it's amazing that such a small part of your brain is so important in the way you make decisions. The hippocampus came to prominence when this young man, age 27, received an operation to cure his epilepsy in 1953. The operation removed his hippocampi and other parts of his temporal lobe. The operation was very successful at curing his epilepsy, but it came at great cost. In essence, this person lost the ability to form new memories of his conscious experience. While he was alive, he was known as H.M. He died in early 2000s, and we now know his real name was Henry Mollison. Henry was well aware of his memories of childhood, but every time he met his doctor, he had to be reintroduced. He'd remember the doctor's name during the course of the session, but the next day, had to be reintroduced all over again. Henry could make certain memories. For example, he could learn drawing and coloring tasks. So he had procedural or motor memory. But making memories about his experience, something called episodic memory, and using those memories to make decisions was way beyond Henry's capability. Events like these brought the hippocampus into the crosshairs of intensive research. The hippocampus had been known to neuroanatomists since the 16th century. In fact, the first guy that described the hippocampus actually thought it looked like a silkworm. The hippocampus from a human is shown on the left here, and a nice cuddly seahorse is shown on the right. The neuroanatomist changed his mind and said after further inspection, well, it does look like a seahorse. So being a good neuroanatomist, he forged a name from the Greek, and voila, we get a new name for a very, very important part of your brain. Fairly recently, there's been a major discovery about the hippocampus, and that is the discovery of hippocampal place cells. These are cells which are like GPS cells. After a rat has explored some space, like this S-shaped track here, you find brain cells that are active when the rat is at a particular point in space. For example, if we record the neurons in this rat's brain and we let him run down the track, when he gets to this yellow section of track, we could see specific neurons become active. The neuron's burst of activity might sound like this. Then later on, when the rat got to the orange part of the track, a different set of cells would burst like this. So there would be a population of cells within the rat's hippocampus that would preferentially burst when the rat was at a particular place on the track. By convention, we usually color the neurons' activity. They're not really yellow or orange, but it helps our understanding of what they do if we color them uniquely. I assert when the yellow cells are firing here, the rat is thinking about being in the yellow portion of this maze. When the orange cells are firing, the rat is thinking about being in the orange portion of this maze. Now, isn't that amazing? Let's see it in real time. What we see here is the actual recording of hippocampal place cells as a rat explores an M-shaped elevated walkway. The position of the rat is going to be denoted by a white light. He's connected to a wire that allows us to record and amplify the neuronal signals from about 10 individual cells. The firing of those cells will be denoted on the left-hand side of the maze. We'll put a little tick mark whenever a particular cell fires. The cells are color-coded so that we can map the activity of the cells against where the rat is in space. Let's see what happens. I'll let the film loop a couple of times, and I draw your attention to the following. Note how the rat is going first up and then left and then down. That's his path through space. As he negotiates this space, the cells follow a particular pattern. Blue cells first, then kind of the greenish ones, then the yellow ones, and the reds, and finally the pinks when he finishes. This sequence of colors map to the rat's path through space. Knowing which cell is firing, we can place the rat on the maze. Knowing the sequence of cell firings, we can map his path through the maze. We can use this information to see a rat think. It turns out that hippocampal place cells fire at times other than just running through the maze, and that fact is going to help us understand how a rat thinks about a path. The other time that hippocampal place cells fire in order is during something called a sharp wave ripple. This ripple is a very short event. It's only about 1/10 of a second long. But during those sharp wave ripples, we see place cells firing in sequence: purple, blue, green, yellow, pink, then brown. We know that place cells actually map to space, and if we plotted those spaces, we would actually trace out a path. The sharp wave ripple shown on this slide is the rat thinking about moving through space. Down, right turn, then up. This ripple is only 1/10 of a second long, much too fast for movement to occur. This is the rat thinking. This kind of thinking is an essential underpinning of deliberative decisions. The second area of the brain we need to talk about is a time-traveling reward system. The reward system of your brain is actually tied to a specific neurotransmitter. Recall that neurotransmitters are those chemicals that one neuron dumps out on another to influence its behavior. There's several different kinds of chemicals, but the reward system of mammalian brains uses a specific one called dopamine. Oftentimes, the reward system is called the dopamine system. What do I mean that this reward system travels in time? Well, let's look at 3 different events. The first event is represented by the neuronal histogram shown at the top. This shows a record of brain neurons in the dopamine system and how they're firing as things happen. In this experiment, a light is turned on randomly and food is placed into the cage randomly. There's no association between the light and the food. You'll notice that the dopamine system doesn't do anything to the light, but boy oh boy does it go crazy when a reward is dumped into the cage. Remember, your brain has no direct sensors, so it needs an internal representation of reward, and the dopamine system is exactly that. In the middle tracing, we've paired a trigger with that reward. The trigger predicts the reward. Notice that the dopamine system migrates in time and now reacts to the earliest event in time that predicts the reward, in this case, the trigger. The reward system goes off on the trigger, and note that it doesn't go off on the reward. The reward is totally predicted by the trigger, so neuronal activity moves in time to now go off on the trigger only. The bottom takes this a step farther. We're now going to have an instructional signal, or something that basically comes on to tell the animal, oh, by the way, the trigger is going to come on in 1 second. The trigger comes on and then is followed by the reward. Look what the reward system does. It goes off again to the earliest predicting signal, in this instance, the instructional cue. You'll note that the vigor of the response decreases over time. The most activity for the reward system is the actual reward. Something that predicts it, or something that predicts something that predicts it, will also cause the reward system to activate, but in increasingly smaller and smaller levels. Here is a system of your brain that can represent reward and also travel in time. Much like place cells representing mental time travel of space, the dopamine reward system can represent mental time travel of reward. The third and final part of the brain we need to talk about before we put it all together is something called the basal ganglia, shown highlighted in this rotating view of your head. The basal ganglia sit in the middle of your brain. Now there's multiple individual areas, but we don't need to go into them right now. We'll just consider them as a whole. I want you to think about the basal ganglia as a go, no-go system of the brain. Various potential movements or behaviors compete in a race condition within the basal ganglia. The first one that gets to a threshold gets committed to behavior. The other potential behaviors are suppressed. Let's see how that works. We'll consider two potential actions, turning right or turning left. We're going to look at a slightly different metric of neuronal behavior called a heat map. In a heat map, the color relates to how many neurons are active and excited. The warmer the color, the greater the activity. Deep reds mean lots of neurons are firing. Deep blues mean very few neurons are firing. In this diagram, we map neurons in the basal ganglia associated with either turning right or turning left. Each trace is aligned with the arrow that points with time. There's probably 100 or so neurons represented here, and we're following them in time. We see many significant phases. The first is both potential actions, so activity early on. Activity builds for both choices until one of the actions crosses a threshold. Once it crosses that threshold, that potential action is committed to behavior. It will take some time before the behavior is actually expressed. Movement objects must be formed, signals have got to be sent out to the muscles, etc. The prime point I want to make with this slide is that 1, potential actions are all simultaneously active. 2, one action gets to a threshold before any other. And 3, that threshold crossing action is the one committed to behavior and expressed. I also draw your attention to the non-expressed movement. It goes very, very blue. That means that potential action is being suppressed. That's a hallmark of this system. One potential action hits a threshold, it's committed to eventual behavior, and the other actions are suppressed. This effect could be important in obsessive-compulsive behaviors, situations where one action is chosen to be done over and over and over again in order to suppress a different behavior and its associated emotions. But let's just keep this simple. Right now, the main points here are multiple actions being represented, one hits a threshold for action, and the other one, and that's the one committed to behavior. Let's put all this together and watch one of our favorite rats as she moves down to a choice point, making a deliberative decision. In this maze, choosing the green path has consistently been paired with food. Turning to the right is the path to reward. No food has been paired with turning to the left. That's the reddish path. What is going through her brain as she gets close to the choice point? Well, her hippocampus, using sharp wave ripples of place cells, mentally travel down each choice path. Turn right and there's food. The reward system, which can also travel in time, evaluates that thought and produces a burst of activity that is fed to the basal ganglia. Her hippocampus will also mentally travel down the left path. No reward, no burst of activity from the reward system, and little is fed to the basal ganglia. The basal ganglia as a group evaluates turning right versus turning left until one action exceeds a threshold. Turning right ultimately gets to the threshold first via activity of the reward system, and turning right then gets committed to behavior. A movement object will be expressed, muscles will point her towards the right, and she'll scamper down that right-hand part of the T maze, and the left-hand turn will be suppressed. Isn't that awesome? Let's see some of these cells in actual operation. We are viewing a rat in a self-returning maze from above. He will run down the center part of this maze and then make a right or left turn, then come back up to the top. He'll then run down the path again. The film has been edited to show alternating choices, first to the right and then to the left. We'll look at some of the cells that are active as the rat is deciding what to do. See if you can use the actual activity of the cells to predict which way the rat is going to turn. Listening to those cells, I hope you reached the conclusion that they were active and bursting when the rat was going to go to the left. The behavior of these cells demonstrates what we've talked about today, the rat brain making a decision. Time now for Homer to join us and talk about the two main points of this section on deliberative decision. Homer, in his own unique way, says that even rats have a brain that can travel in time. This turns out to be of fundamental importance in the way to understand our brain. Our brain can move us around in time and space just like a rat's brain can move them around in time and space, not only for physical space, but for reward. Activity from those events can then feed other systems that can determine which particular potential action is actually going to be expressed in the movement of muscles. But Homer also has a second point. And if you know anything about Homer, you know he's a bit of a lazy guy. So what he says is, sure seems to take a lot of effort in making this kind of decision. And he is very, very right. Your brain takes 25% of the caloric load on your body. In other words, 25% of the energy in your body is spent on the workings of your brain. Mother Nature is very careful about how you spend energy. So that brings us to the fourth kind of decision. Habit. Habits are decisions that your brain has delegated and really not much engaged in anymore. Habits occupy an amazing amount of our time, and it turns out they're quite useful. Almost half the behaviors that you do on any given day are habits. I bet you didn't know it, but there are psychologists who measure how we spend our day, and their research shows that about 45% of the behaviors humans do on any given day is habit. In nature, the percentage for wild animals can be even more. If you don't think you're a creature of habit, try changing your shower routine. Your shower or bath routine is a highly stereotypical behavior sequence for most of us. That means that we really don't deliberate over each individual behavior we're doing. Each behavior seems to be cued by the behavior just before. First wash this bit, then that bit, then the other bit, etc. We tend to have rigid routines when we bathe, when we drive to work, tie our shoe, etc. We are all creatures of habit. The benefit of habit is reduced energy load on the brain. How this reduced energy load is accomplished is related to the reward system. The reward system is sensitive to surprise. We've seen the reward system activate when unanticipated reward happens. That's shown here. The reward system detects the fact that something significant has happened that wasn't predicted. Neuronal rates go up and we see an increase in the histogram on top. Pair that reward with a predicting stimulus and we see that the reward system accelerates its response to the stimulus that predicts the reward, but keeps firing along at a steady pace when the actual reward is delivered. There was nothing surprising. Reward was predicted, therefore the system keeps on doing what it was doing. Now, suppose we predict a reward, there's a signal, in other words, that says a reward is about to come, and then no reward happens. In this instance, the reward system ceases firing. That means the reward system reacts when there is a surprise. This has implications on the overall activity in your brain. When your reward system is changing, either accelerating or decelerating from its normal rate of fire, your brain lights up. Your brain is very active when your reward system is surprised. The origin of the reward system is shown on the lower right. It's in your brainstem, the ancient part of your brain. This part of your brain controls breathing and autonomic functions, the things that you don't have to pay attention to. Output from the reward system innervates wide-ranging parts of the front part of your brain, the frontal cortex. This is where outcomes are evaluated. So when your reward system is surprised, it activates huge portions of your neocortex and your brain is chewing up energy like crazy. That's good when you can't predict what's going on in the environment, but when you can predict what is going on in the environment, your brain could use a different strategy. It could use the simplest set of stimuli in the environment that predict the future. Like in your shower routine, you just use a simple movement, washing your hair, to cue the next movement, washing your face. Is this really what happens in real life? Well, yes, and we can show it experimentally. The experiment deals with a rat in a maze. Surprise, surprise, right? It helps to imagine that the maze is labeled with compass points. Before we describe the experiment, I want to ensure that you have a practical view of the maze itself. It looks like this. Note that the rat can see all sorts of stuff in the room, and the rat could use them as signposts in making a turn. So from the rat's perspective, the rat may not be turning to some sterile point of the compass to go west or east. The rat could be turning to the red chair or some other landmark in the room. This perspective is important in understanding what happens in the next experiment. We'll train the rat that food is always in the east. So if we start the rat in the south part of the maze, she would run down, turn right, enter the east section of the maze, and get a food reward. Periodically, we're going to probe how the rat is learning. We'll change the start location. We'll start her on the north side and then observe which way she turns in the maze. The rat can use one of two strategies in deciding which way to go. One strategy, known as a place strategy, means that the rat will use extra maze cues, like chairs in the room, to deliberate and determine which way is east. She will then turn that way. If she was started in the north, then she turns left to get to the east. If the rat is using what is called a response strategy, she's going to do whatever the response she's done most of the time in training, turn right. In this instance, starting from the north, she would turn right and wind up in the west side of the maze. Well, what does she do in training? Well, it depends on whether the habit has been formed. Early in training, when the rat is just initially learning, she takes a place-oriented decision. That's a deliberative decision and runs to the east. Why? Because early in training, her reward system has got her brain lit up. Her hippocampus is moving her around in time. The basal ganglia is integrating information from the frontal and the frontal cortex is evaluating outcomes. This rat is fully aware and processing all the stimuli in the room. So she goes to a place, the east. If we continue training, running down the maze becomes almost automatic. Now when we start her in the north, we find the rat takes an associative decision. Turning right has been paired with finding food so many times, the rat's not thinking. She's running down, she gets to an intersection. The normal thing to do is turn right, and that's what she does by habit. The rat is only using a small part of her brain, part of the basal ganglia called the caudate nucleus, that's shown in green here. The point is that she's not really processing many stimuli. Running down the maze means turn right to get food. From an energy use perspective, and from showing us how habits form, this experiment illustrates exactly what happens in the formation of habit. We go from where our brain has been awoken and lit up by surprising events, we're fully engaged and are cognizant of all the stimulus around us, to only using a small part of our brain to figure out what to do next as we get trained on a task. As beneficial as habits might be for energy utilization in your brain, they're also the source of much human and gerbil misery. Because habits, when formed, are very, very difficult to break. Your brain is on autopilot. Habits can be maladaptive, and it's very, very difficult to break chains of autopilot behavior because your brain is really not evaluating other options. It's not deliberating anymore. It's performing automatic associative decisions where one step leads to the next, and at the end of some of these chains is not a good place. Time now for Homer to weigh in again at the end of a section and give us his observations of note. The first is that Homer really likes habits. They help his simple brain not get too tired. Homer is not one to really apply himself most of the time, and Homer is absolutely a creature of habit. He manages his brain at a very low energy level, and that's just fine for Homer. We wish him well with that. But Homer also notes that once bad behaviors turn into habits, they are rigid and therefore very difficult to change. This is one of the challenges of modern behavior, and I think Homer's got it nailed here. The study of habits, and especially the way of breaking habits, can offer great hope to segments of our population who are really in need. I'd like to close our seminar today with some overriding thoughts. First, 3 of the decision systems we have talked about today, reflex, associative, and habit, are all automatic. Your brain is wired to do this. Yes, you can override reflexes, and there's ways of modifying habit, but in general, these decisions systems are automatic. They reflect the way your brains are wired by Mother Nature. They're not going to change for thousands of years. Most of the time, say 80% or so, they seem to work well. But when the ultimate behavior out of these systems are ill-suited to the facts of modern life, it's not necessarily because people are evil. It's because their brains are wired that way. To make progress, we need to switch to manual mode. This is a deliberative choice or decision to override what our automatic brain systems are doing. We can use these deliberation systems to address automatic bias and other kinds of associations that our brains naturally make. One example comes from modern symphonies. People generally tend to pick groups that are similar to themselves. That's the us group or the in group. So if white males already in the symphony choose auditioning players, white males are going to tend to pick white males. Modern symphonies have found that blind auditions accommodate and address such automatic bias. Performers audition behind a curtain, therefore the evaluator doesn't know the gender, doesn't know the race, doesn't know the ethnicity of the performer. This has turned out to be a wonderful way of eliminating gender and other kinds of bias. A similar process is now being used by NASA to allocate time on the Hubble Space Telescope. It is targeted to eliminate gender, ethnic, and university bias. And then finally, this process is being tested in the legal system to address implicit bias. The key thought here is to use our deliberative brain to override our bias brain. An afternoon of training is not going to eliminate an evolutionary skill hundreds of thousands of years old. Only other parts of our brain devising new modes to counteract this natural bias is going to address the situation. And I'm glad we're starting to make real progress using such approaches. This concludes Seminar 2, The Decision to Act. I hope you enjoyed it. Let me foreshadow the topic of Seminar 3, The Structure of Memory. Memories are complex, multidimensional, slippery concepts that have several processes within the brain. They also have a structure within the brain. We'll talk on the next seminar about the essential characteristics of memory. One type of memory is like a story from Proust, the French writer. Proust wrote several volumes and thousands of pages about a memory that came from a fateful encounter of a famous Madeleine with a cup of tea on a cold winter's day. His memories came out in rich, detailed patterns. However, this is but one way memories could be structured. Are there others? Well, yes, and there are different brain structures which bring them about. A good analogy is the totem pole of Pacific Northwest Indians. Totem poles are not an elaborate reconstruction of a story as told in the pages of a book. They're the essential elements of the story as carved on a totem pole. To give a familiar example, the totem pole for Goldilocks and the Three Bears would be a pole that has a bear, a bowl of porridge, and a bed carved on it. The story would be reconstructed from these symbols. Now, of course, that means two different people might tell the story two different ways, or the same person on two different occasions might tell the story in two different ways. We'll see how memory structures relate themselves to brain structures in underpinning both Proust-like stories and Pacific Northwest totem pole-like stories. Please join me next time to see the fascinating story of the structure of memory. This is Steve Soltwick.
mata mi corazón.